Hello AP Chemers, we're continuing titrations. So this time we are going to look at the titration between a weak acid and a strong base. So we have 50 milliliters of 10th molar acetic acid, which is a weak acid, and we are going to titrate it with 10th molar NaOH, which is a strong base, both 10th molar. So we are going to determine the pH at different points of our titration. We're going to start with before any NaOH is added. And so I have my flask. Right now I only have in its just acetic acid, so CH3COOH. I have 10th molar of that and I have 50 milliliters of it. So, since I only have a weak acid in my flask, how do I find the pH of a weak acid? Well, you start by writing the dissociation equation for the acid. It's an equilibrium H plus and acetate ion. And because it's an equilibrium, you're going to do an ice chart. It's 10th molar to start with, 0 and 0, minus x plus x plus x, so 0.1 minus x, x and x. Then you write out your equilibrium expression. So the Ka, which is 1.8 times 10 to the negative 5th, you probably memorized the Ka for acetic acid by now, since we use it so much, is x times x over 0.1 minus x, x being our H plus. If you were to calculate x, you would get 0.00133 molar. That is your H plus concentration. And so the pH is negative log of that, which ends up being 2.88. So that's my pH of just my acid in my flask there. So now let's take a look at what would happen to the pH if I were to add 10 milliliters of NaOH. So now in my flask, now I have 50 milliliters of my acetic acid that were there originally, and now I've added 10 milliliters of NaOH. Well, what happens when you put NaOH with acetic acid? A reaction happens. So we need to write out our reaction between those two first. So I'm going to do that. Now, my NaOH, my Na plus is just a spectator there. It doesn't really do anything. So if you want to write NaOH, you can, but I'm just going to write OH minus for it. It's up to you. My acetic acid is CH3COOH. That is a reaction that nearly goes to completion. Again, any acid-base reaction, the K will be very, very big, and so you can look at it as if it's a reaction that goes to completion. My OH minus will grab an H plus from my acetic acid to form water, and then I will also form some acetate ion. So I'm going to start with how much I have, how much reacted, and what's left over. So I have 50 milliliters of my acetic acid, which is 10th molar, so 0.05 liters times 10th molar would be 0.005 moles. So I'm going to write that down. Don't care about my water, really. I do care about my hydroxide there. I have 10 milliliters of 10th molar, so that ends up being 0.001 moles. Like I said, I don't care about my water, but my acetate starts out at 0. Let's look at my limiting reactant here. Looks like my hydroxide is my limiting reactant, and that's how much is going to be used up. So minus 0.001 moles. Minus 0.001 moles. and I'm forming 0.001 moles. Now, why is it important that I add that in here when before I didn't? When I did strong, I never really cared about what my products were. Well, that's because my products were H2O, which is a liquid, and it's a pH of 7. I don't really care about it. But my other product for strong in the last example that we did in the last video was NaCl. Na plus and the Cl minus ions do not undergo hydrolysis. They do not affect the pH. However, the acetate ion can undergo hydrolysis if I need it to, or if I look at it, it will undergo hydrolysis. And so I do kind of care how much I have from this one. So anyway, at the end of this reaction, all my hydroxide is used up. I end up with 0.004 moles of my acetic acid, and I end up with 0.001 moles of my acetate. So, at the end of this reaction, all I have left is some acetic acid and acetate. A weak acid and its conjugate, or a weak acid and its salt. How do you find the pH of a weak acid and its salt? Well, you have two options. You can do an ice chart. You can write the dissociation for the acetic acid and do an ice chart like this. So you would write, I have acetic acid CH3, COOH, dissociating into H plus and CH3, COOH, acetate. There we go. COO minus. So I have some of this. I have some of this. I do an ice chart and figure out what my X is, right? Or what's the other option? A little bit easier is the Henderson-Hasselbalch. So we'll use the Henderson-Hasselbalch just to save us some time, but either one is acceptable. Now these are moles. I want to convert to molarity, so I can either do an ice chart or the Henderson-Hasselbalch. So I'll do that real quick. My total volume, I have 50 mils of acetic acid and 10 mils of NaOH, so my total volume is 60 mils, which is 0.06 liters. So I'll divide both of those by 0.06 liters. For my acetic acid, I end up with 0.067 molar, and this one is 0.0167 molar. So I'll use my Henderson-Hasselbalch. If you remember, its pH is equal to the pKa plus log of the conjugate base concentration over the acid concentration. So that is equal to, pKa is negative log of the Ka, so negative log of 1.8 times 10 to the negative fifth, plus log of my conjugate base is my acetate. It's 0.0167 molar. My acid is my acetic acid. It's 0.067 molar. And so that ends up being 4.14. And that's my pH. So I start with just my acid at a pH of 2.88. I've added 50 milliliters, 10 milliliters of the NaOH, and now I'm at 4.14. All right, now let's look at if you had 25 milliliters of the NaOH. So let's do that. So right now I have my 50 mils of my original acid, the acetic acid, and I've added 25 milliliters of the NaOH in my titration so far. So what's going to happen? Those two are going to react together. Let's write our reaction. OH minus. Again, I use OH minus because it's a strong base. If you want to use NaOH, you can, but I'm just writing the net ionic there. CH3, COOH is my acid, This is a complete reaction. You get water and acetate ion again. All right, let's do my moles. Now that I've added 25 milliliters, so 0.025 liters times 10th molar, that gives me 0.0025 moles. My acetic acid, I started out with 50 mils of 10th molar, so that is 0.005 moles. Don't care about my water. My acetate, I started out with 0. I haven't formed any yet before my reaction. Let's see which one's my limiting reactant here. Looks like this number is lower, so that's what's going to get used up. So minus 0.0025 moles and minus 0.0025 moles and plus 0.0025 moles. At the end, my hydroxide is used up. This is 0.0025 moles, and this is 0.0025 moles. So let's look at what's left over at the end. Looks like I have some acetic acid and some acetate, so weak acid and its conjugate, or weak acid and its salt, however you want to look at it. And so to find the pH of a weak acid and its conjugate, you write out your dissociation equation. Of your acid, CH3, COH, H plus and acetate ion. And you do one of two things. Since you have both an acid and its conjugate, you can either do an ice chart or the Henderson-Hasselbalch. Henderson-Hasselbalch is much easier. Either way, you have to figure out what your concentrations are, because we just have moles here. I have 50 mils of acetic acid, 25 mils of NaOH. That's a total of 75 mils, so divided by 0.075 liters. Let's see, my concentration for the acid ends up being 0.033 molar. And this is the same concentration, 0.033 molar. Can you tell already what will happen? Some of you can. Let's look. So, according to the Henderson-Hasselbalch, pH is pKa, which is negative log of the Ka. 1.8 times 10 to the negative fifth, plus log of conjugate base, which is 0.033 molar, over the acid 0.033 molar. Look at that. I have my conjugate base and my acid same concentration. So this is equal to 1. Log of 1 is 0. So the pH is equal to the pKa. And so that is going to be equal to 4.74. When the pH is equal to the pKa, that means that this is half neutralized, because that means that my conjugate base and my acid are equal in concentrations. That's going to happen when I have half of my amount of acid used up. So let's look at this again. If I use up half of this amount, I would form the same amount of the conjugate. Those two concentrations are going to be the same, and so the pH is going to be equal to the pKa, because these are going to be 1 and log of 1 is 0, and so pH is equal to pKa. Again, that means half neutralized. What does that mean? That means I've added enough base to use up half of my acid. And so if I wanted to reach the equivalence point, I need to double my hydroxide amount. So if 25 milliliters reached the half neutralization point, that means I need 50 milliliters to neutralize it or to reach the equivalence point. By the way, we say to neutralize it, but that means to reach the equivalence point, which does not mean we're going to have a pH of 7. Neutralization, from the name, you would think it means neutral, but it doesn't. It's a little bit deceiving. So let's write this down because that's kind of an important thing. This is half the neutralization point. Let's say half neutralized. The pH is equal to the pKa. This is when your moles of acid are equal to the moles of its conjugate base. The moles of the weak acid are equal to the moles of its conjugate, meaning that the acid here and its conjugate are equal, not the acid and the base reacting are equal. That would have been the equivalence point. When those two are equal, that's the equivalence point. When those two are equal, that's half the equivalence point. All right, let's look at when we add 50 milliliters of base. Well, oops, you can kind of already tell, right? Because we just said 25 milliliters is half neutralized, so 50 milliliters would be neutralized. So let's try that one. All right, so now I have 50 milliliters of my acetic acid and 50 milliliters of the NaOH. What's going to happen? A reaction between the two. So let's write out our reaction. So any titration problem, you're going to write the reaction between the two, figure out how many moles you have, how many moles are used up, what's left over. Then you look at what's left over and to try to find the pH of the species that are left over. So let's do that. I have hydroxide that I'm going to use OH minus to represent because it's a strong base. I'm going to react that with some acetic acid, CH3COH. I'm going to form water and some acetate ion. I have 50 mils of 10th molar NaOH, so that's 0.005 moles. The acetic acid, I also have 50 mils of 10th molar, so 0.005 moles. Don't have any water or acetate. Moles of my acid are equal to moles of my base. That means I'm at the neutralization point. But remember, the pH is not always 7 when it's the equivalence point. So, no limiting reactant here. Both of them get used up. Minus 0.005 moles, minus 0.005 moles. Don't care about my water. Plus 0.005 moles. At the end, I have no sodium hydroxide, I have no acetic acid, but I do have some acetate ion. Let's go ahead and divide by the total volume just so we can get molarity. It's 100 mils, so 0.1. So that gives me 0.05 molar. So, after this reaction occurs, and I've reached the equivalence point, I'm going to go ahead and point that out. This is the equivalence point because my moles of acid are equal to my moles of base. That's these two right here that are reacting are equal to each other. I've reached the equivalence point. But my pH is not 7 in this case. Why is it not 7? Well, I form water, which has a pH of 7, but I also form acetate ion, which can undergo hydrolysis. And so since that's my only species that is left in the water, the way to find the pH of an ion is by doing a hydrolysis reaction and doing an ice chart for it. So let's do that. So my acetate ion, the CH3COO minus, is going to react with water. That's going to be in equilibrium. I'm going to form some acetic acid and some hydroxide ion. And I need to do an ice chart here. So this is 0.05 molar. Don't care about the water. I don't have any acetic acid left. I don't have any hydroxide. Minus x plus x plus x. 0.05 minus x, x, and x. This is forming a base, so I need to look up the Kb for acetate ion, and I write my Kb expression. So my Kb is going to be the concentration of the acetic acid times the concentration of the OH minus over concentration of the acetate ion. My Kb in this case, I believe, is 5.6 times 10 to the negative 10th. That is equal to x times x over 0.05 minus x. X is 5.29 times 10 to the negative 6 molar. And my x here is my hydroxide concentration, not my H+. And so I can find my pOH first. Ends up being 5.28. And so my pH is going to be 8.72. So what if I keep adding sodium hydroxide to this titration? Well, I've already reached my equivalence point. I've used up both of these and just formed acetate. If I were to add more of this, so if this number was larger than that number, then my acetic acid would be my limiting reactant, and at the end I would end up with some sodium hydroxide left over and some acetate that formed as well. So I would have some hydroxides from here and also some hydroxides from here, but to be honest with you, if you are left with that situation, you can just ignore the acetate because the amount of hydroxide that you'd form from the hydrolysis is very, very, very minimal compared to the amount of hydroxide that you have from the NaOH. So if that is the case, if you ever find a problem like this where you end up with some strong base at the end along with an ion that can undergo hydrolysis to form a base, ignore that. Just use this concentration to find your pOH and therefore your pH. Now, what if I keep adding more and more and more and more? What would be my pH at the very end? Well, let's take a look at my titration curve here. So let's see what would have happened. So initially, I had my acetic acid by itself. It had a pH of 2.88. The pH increases very, very, very slowly as I add my NaOH. There's my half neutralization point. That's when my pH is equal to my pKa right here. I add more and more base, and then suddenly it shoots up, and then it continues to rise slowly, 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 and then it reaches almost a straight line. What would this be approaching? What is my limit there? That would be the pH of just my pure base. So if I've added gallons and gallons of base, I can't reach a pH above that. That would be the pH of 13 in this case because I'm titrating with 10th molar NaOH. If you were asked to draw a titration curve for a titration, what you want to do is make sure you know your initial pH, make sure you know the pH of just the base that you would add, and then make sure you know what your equivalence point is. In this case, Our pH was 8.72, which is basic. Again, because of that acetate that undergoes hydrolysis to give off OH minuses. If it's a weak species, you also want to know what the half neutralization point is, because that will be the pH is equal to the pKa there. One thing to note in this curve is notice how sharp this is compared to this one. Is kind of really curvy. The stronger your acid or base, the sharper your line will be, or the sharper your curve will be. The weaker the species, the more curvy it's going to be. So if you were given this, even without any numbers, you should still be able to tell that this base is pretty strong, this acid is weak. If you are given this number here, you should also know that this is a strong base, weak acid, because your pH at the equivalence point is higher than 7. All right, let's do the opposite now. Let's look at a strong acid with a weak base. So I have 20 milliliters of 10th molar NH3, which is a weak base, titrated with 0.05 molar solution of HCl. So in this one, I'm doing the opposite, actually. Now I have my NH3, or my base, in my Erlenmeyer flask, and I'm adding HCl to it. So this one's going to be one of those Z curves as opposed to S curves. So I want to calculate the initial pH of just my NH3. So I have a weak base. To find the pH of a weak base, what do? You write the dissociation and an ice chart. Let's do that. So I have NH3 and water, equilibrium. I get NH4 plus OH minus. I'll do an ice chart. Initially, it is 10th molar. Don't care about water, 0 and 0. Minus x plus x plus x. 0.1 minus x, x, and x. My Kb, which is 1.8 times 10 to the negative fifth. It's actually the same Ka as acetic acid by coincidence, is x times x over 0.1 minus x. In this case, x ends up being 0.00133 molar, and in this case it's my hydroxide ion concentration. And so I can find my pOH. First, it's going to be 2.88 or 2.87. So my pH is 14 minus that, which ends up being 11.33. All right, now I'm going to add some of that HCl. I'm going to add 2 milliliters of HCl. So if I have some HCl with NH3, what would they do? They would react together. First step is write out your reaction. So for my HCl, since that's a strong acid and my Cl minus is just a spectator, I'm going to use H plus instead of HCl. I'll add that to NH3, my product. Again, this is an acid-base reaction, so nearly goes to completion. NH4 plus is my product. I'm going to figure out how many moles of each of them I have. And so I have 20 milliliters of 10th molar NH3, so that's 0.002 moles. And for my HCl, I have 2 milliliters, but it's only 0.05 molar. So 0.05 molar times 0.002 liters would be 0.001 moles. And none of the NH4 plus. If you look at the H plus and the NH3, looks like the H plus is my limiting reactant. It's going to be used up, so minus 0.001 moles and minus 0.001 moles and plus 0.001 moles. At the end of my reaction, I've used up my H+. I have 0.001 moles of the NH3 left, 0.001 moles of the NH4+ left. Oh, I'm so sorry. I think there's a 0 that I messed up with. There is another 0 here. It's actually 0.00. I apologize. I made a mistake. It's for the H+, it's 0.0001 moles, not 0.001. So I apologize about that. Correct that, please. At the end of my reaction, I don't have any H+ left. This one I have 0.0019 moles left. And this one I form 0.0001 moles. I'm going to go ahead and divide by the total volume. I have 22 mils, so divided by 0.022 liters, 0.022 liters. This one gives me 0.0864 molar. And this one gives me 0.0045 molar. All right, let's look at what we have. At the end, I have a weak base and its conjugate. How do you find the pH when you have a weak base and its conjugate? Two ways. First, you write out the dissociation of your base, and then you either do an ice chart or you do a Henderson-Hasselbalch. So I'm going to do a Henderson-Hasselbalch because it's a lot easier. Since this is a base, it is more correct to do the Henderson-Hasselbalch with the base equation, which says POH is equal to the pKb plus log of the conjugate acid over the base. So the POH is equal to negative log of the Kb, which is 1.8 times 10 to the negative fifth, plus log of my conjugate acid is 0.0045 molar. My base is 0.0864 molar. And so my POH ends up being 3.46, and therefore my pH is 10.54. The next question is slightly different. Instead of giving us a certain amount of acid and a certain amount of base and asking us for the pH, they are asking us what would the volume of HCl that's required to neutralize my NH3 be? And also, what is the pH at the equivalence point? But they don't tell us what the volume is of the HCl that I need to reach the equivalence point. They're asking for that. So let's try to think about this. My reaction is still between my HCl and the NH3, so let me write that down first. So I have my H+, which is my acid, or HCl, plus my NH3, that yields NH4+. Now, the one thing that I know for sure is how much NH3 I have, because that never changes since it's in my flask. And we said that I have 0.002 moles. Now it's asking us about the equivalence point. At the equivalence point, or which is what I need to neutralize it, and again, this is misleading. Neutralize it means moles of acid and moles of base are equal, or the equivalence point. It does not mean pH of 7. So anyway, to neutralize it, which means moles of acid and moles of base are going to be equal to each other, that means I also need 0.002 moles of my acid. So that is when I reach my equivalence point, or when it's neutralized. So if that's what I start with 0 of my NH4+. My change would be that I use up that amount minus 0.002 moles minus 0.002 moles and plus 0.002 moles. So at the end, if I've reached my equivalence point, this is 0, and this is 0.002 moles. Now, if I wanted to find the pH that's at the equivalence point, all I need to do is find the molarity of this. This is my only thing that's left over. It's NH4 plus that can undergo hydrolysis. So I need to find the molarity of this and do an ice chart with it for the hydrolysis equation. Problem is, I don't know what the volume of HCl is to tell me what my total volume is so I can find my concentration. That was one of the questions. But I already figured out that I need 0.002 moles to reach the equivalence point. So, since I know the moles and I know the molarity, I can figure out the volume. So let me do that. So at the equivalence point, the moles of HCl are equal to the moles of the NH3, which is equal to 0.002 moles. So my HCl is 0.05 molar. I need 0.002 moles. I can solve for the volume. So I just do 0.002 divided by 0.05. That gives me 0.04 liters of HCl needed. So now that I know that, I can divide my moles of NH4 plus with the total volume. I have 0.04 liters of HCl, and let's see, I have 0.02 liters of ammonia, and so my total volume is 0.06 liters. So that gives me 0.033 molar of my NH4 plus. So at the equivalence point, I've used up my acid and my base. I just have NH4 plus left, which can undergo hydrolysis. So I'm going to write the hydrolysis equation for that. So NH4 plus water, that's an equilibrium. I form NH3 and then hydronium ion. Plus there. My ice chart is going to start with 0.033 molar. Don't care about the water. 0 and 0. Minus x plus x plus x. 0.033 minus x. X and x. Since this is giving me an acid, I'm going to write the Ka expression for NH4 plus. It is the concentration of the NH3 times concentration of the hydronium ion over the NH4 plus. This is 5.6 times 10 to the negative 10th is equal to x times x over 0.033 minus x. X ends up being 4.3 times 10 to the negative 6 molar. In this case, my x is my hydronium ion. Same thing as H plus. So I can find the pH. It's negative log of that, which is 5.36. And that is my pH at the equivalence point. It is acidic because I have a strong acid neutralizing a weak base. Last thing they ask me in here is to construct a titration curve using the above data. We want to mark the equivalence point and mark the point halfway to the equivalence point. So if I need to draw a titration curve, these are the things that I need here. I need my starting pH, I need my equivalence point pH, and I need my ending pH. So I have my starting pH, it's 11.33. I also have my ending pH. We figured that was 5.36 at the equivalence point. I need my ending pH, as in, if I were to add a whole bunch of HCl, what would the final pH be? What would it approach? And so it approached the pH of my acid by itself, and my acid is 0.05 molar, so negative log of that would be 1.3. Let's write that down real quick. My ending pH would be pH of just the HCl, so negative log of 0.05 is 1.3. All right, so back to my curve here. All right, so I just labeled my axes here. I have my pH on the y-axis, and then my volume of HCl, since that's what I'm adding here. So let's see, my starting pH was 11.13. So should be somewhere here, about there. My equivalence point was after 40 mils, and it was 5.36, so somewhere here. Since I know that my equivalence point happened at 40 mils, that means my half neutralization is at 20 mils, and the pH should be equal to the pKa, which would be, if you were to calculate it, 9.25. So right there. And then my final pH, if I were to add tons and tons of acid, it was 1.3, so somewhere here. And so maybe my curve would look like that. I kind of messed up. It should be a little bit lower here, but you know I can't draw. Something like that. Let me label my different points. So here they are. That's my starting pH, 11.13. My halfway neutralized, my pH is equal to pKa, or you can think of it as the pOH would be equal to the pKb. So you could do it that way and figure out the pH from there. The equivalence point is 5.36, again, because it's a strong weak, and my ending pH is 1.3. Also notice how sharp this part is, because it's a strong acid, and then how curvy this part is, because it's a weak base. Let's try a couple more quick problems here. So I want to determine the pH at the equivalence point when 100 mils of 0.25 molar NaOH is added to 10th molar acetic acid. So I have my flask, I have some acetic acid and NaOH. Now they don't tell me how much acetic acid I've added, but they do tell me it's at the equivalence point, which tells me my moles of acid and my moles of base are equal to each other. So what I could do is I could figure out how many moles of base I have. I have 100 mils of 0.25 molar, so that's 0.1 times 0.25, so 0.025 moles of my NaOH and 0.025 moles of my acetic acid as well. Since I know that my acetic acid is 10th molar, I can figure out that I have 100 milliliters of, 250 milliliters of my acetic acid. Here's my calculation to figure that out. I have 10th molar. I know I need 0.025 moles over X liters, so it ends up being 0.25 liters. So let's write out our reaction between my acetic acid and my NaOH. So my NaOH is a strong base, so I'm going to use OH minus plus my acetic acid. I form water and acetate. So 0.025 moles, 0.025 moles, and 0. Don't care about the water. Minus 0.025 moles, minus 0.025 moles, plus 0.025 moles. So at the equivalence point, I don't have any of those, and I have 0.025 moles of my acetate. If you want to do part of this in your head, that's fine. It's kind of obvious that I would end up with the same amount of moles of the acetate. But anyway, at the equivalence point, I don't have any of these. I only have acetate ion, which can undergo hydrolysis, and that's how I find its pH. So I'll write the hydrolysis equation now. So that with water, it will grab an H plus from the water to form acetic acid, and it will form some hydroxide ion. I would need to divide by my total volume here to find my concentration. So 0.025 moles divided by, I have 100 milliliters of NaOH, and I have, we figured out 250 milliliters of acetic acid, so 0.35 liters is my total. That gives me 0.0714 molar. So this is 0.0714 molar. Don't care about the water. 0 and 0. Minus x plus x plus x. 0.0714 minus x. X and x. My Kb expression. 5.6 times 10 to the negative 10th is equal to x times x over 0.0714 minus x. I'm going to calculate x, which is my hydroxide ion concentration. And I apologize, I just added this problem to your notes, and I don't have it in mind. And I don't have a calculator at home right now with me, so I don't know what the x will be. So you guys figure out what the concentration of the OH minus is, and the POH and the pH eventually. But definitely my pH at the equivalence point will be basic. It should be higher than 7. So I'm going to let you guys finish this off. Let's look at the next problem here. This one says, a weak diprotic acid was titrated with a base. Now, even if it doesn't tell me that this is diprotic, I should be able to look at my titration curve and figure out that it is. How do I know that? Because there are 2 equivalence points. And I know that because there are 2 like inflections with a part that's almost vertical. So there is my first equivalence point, and here's my second equivalence point. If it was triprotic, guess what it would look like? It would, look like this, where there will be a third equivalence point right there. So I'm going to go ahead and erase that. Now, what it's asking for is, it says from the titration curve, we want to calculate pKa1 and pKa2. What is that? That's negative log of the Ka for the first H plus of that acid and for the second H plus of that acid. Well, how do you know that? Well, the pKa is equal to the pH when it's half neutralized. So let's look at the first one. Here is my equivalence point. It looks like it's at 8 milliliters of base. So what I do is I go to halfway to that. So instead of 8 milliliters, I go to 4 milliliters. Let's see if I can try to get to about 4 is right there. And so I go up to here, and then I read what my pH is. And so I am kind of estimating here, maybe it's a pH of about 3 or something like that. Now, if you were doing this on the test, the numbers would be a little bit clearer or easier to read, and also they'd give you more leeway. So I'm going to say that my pKa1 is going to be equal to about 3 or so. Okay, now let's look at pKa2. So what you do is you go to half the second equivalence point. So right here is my second equivalence point. It's at 16 milliliters. This was 4 milliliters down here. So what you do is you look at halfway between those. So 16 and 4, halfway to that. I'm sorry, 16 and 8, halfway to that would be 12. Because this is where my first equivalence point is. This is my second equivalence point. So you look at halfway between those 2 points. And so that would be about 12 or so. Let me mark that. So right here at 12 milliliters. So you go to 12 milliliters and you read what the pH is right here. And so, I don't know, that looks maybe like maybe a 9-ish or so. It's kind of really hard to read on this, but it should be close to about 9. It's definitely above 7 there, but, you know, I'd accept 8, 9, maybe even 10. Any of those would be acceptable. All right, next is a chart that I just added to the notes this year because I felt like, you know, titrations are really confusing. There's so many different calculations and so many ways that you would find the pH, and it just depends on if you have a strong or weak or, you know, at the end, is it the equivalence point? Is it halfway? Is it after? What's going on? So here are the steps to find the pH whenever you're doing any titration calculation. So what you do is, first of all, you look at your acid and your base that are reacting together. You write the reaction between the acid and base. And it's always one arrow because acid-base reactions have very high Kas. They go to completion. Next, you determine the moles of the acid and the base that you're given initially. You determine which one's the limiting reactant. Subtract that from everything, add it to the products, figure out how much is used up, what's left over. And then, at the end, look at the substances that are left over. Some of them would be used up. You don't look at those. Look at the ones that you actually have remaining. And depending on what kind of substances are left over, you determine how to find the pH. So, let's go through a list. Let's say you've used up everything and all you have left is some strong acid, like HCl, for example. That's all you have left. Well, in that case, you just use the molar concentration of the HCl. You say that's the concentration of the H+. You do pH is equal to negative log of that H+. Okay, what if what you're left over with was a strong base, like NaOH, for example, or, you know, OH-. Well, again, use the molar concentration for the NaOH. That would be the concentration of the OH-. So you find the POH from this, and then pH would be 14 minus the POH. That's pretty straightforward. What if you're left with something like HF? That's a weak acid. Well, how do you find the pH of a weak acid? You got to do the dissociation of the acid. So HF yield double arrow because it's equilibrium, H+ and F-. Do an ice chart for your acid dissociation. What if you're left with something like NH3? That's a weak base. Well, how do you find the pH of a weak base? Same thing, ice chart for the base dissociation. What if you're left with something like HF and F minus, or like acetic acid and acetate, or something like that, where you have a weak acid and its conjugate? Well, you could either do an ice chart, or easier, you could just do a Henderson-Hasselbalch. What if you're left with like ammonia and ammonium, a weak base and its conjugate? What do? Again, you could do an ice chart, or you could do a Henderson-Hasselbalch. What if you're left with something like a neutral salt, like NaCl? No need for any calculation. That's a pH of 7. That's pretty easy. That would be a strong titration at the equivalence point. What if you're left with an acidic salt like NH4Cl or just NH4+? Well, that undergoes hydrolysis, and so you write the hydrolysis of that cation and you do an ice chart. What if you're left with a basic salt like KF or F- by itself? Again, hydrolysis of the anion and then an ice chart. So hopefully this kind of helps. Always write out your reaction, figure out how many moles, what's your limiting reactant, what's used up, what's left over. Look at what's left over, and depending on what substance is left over, this is how you determine the pH. So hopefully that kind of helps.